find the horizontal asymptotes for the functions. So on this first page we have a couple examples. F of x equals the square root of 3x squared plus 2x plus 1 all over 4x minus 5. And when you start looking at these square roots of x squareds, the funny things happen. This leads you with two different horizontal asymptotes, which is very strange. So the first time around, you want to find the limit as x approaches positive infinity of the square root of 3x squared plus 2x plus 1 all over 4x minus 5. And I'm going to use that equality, that the square root of x squared equals the absolute value of x. And since we're going to positive infinity, this absolute value of x will be x. So I'm going to divide each term in the numerator by x squared, and I'm going to divide each term in the denominator by positive x. So here we go, over x squared, over x squared, over x squared, over x squared, over, in the denominator I said over x, there we go. And this simplifies to the limit as x approaches infinity of the square root of 3 plus 2 over x plus 1 over x squared all over 4 minus 5 over x. Go. This goes to 0, this goes to 0, this goes to 0. It looks like we're just left with square root of 3 over 4 equals y as one horizontal asymptote. The next time around, you want to take the limit as x approaches negative infinity. And so I'm going to call this just of f of x, and I'll write down the division part like this after a brief explanation. Since we're going to negative infinity, the square root of x squared still equals the absolute value of x. But because x is going to negative infinity, the absolute value of x will equal negative x. So we will have the limit as x approaches negative infinity of 3 plus 2 over x plus 1 over x squared, the square root of all of that, over negative 4 plus 5 over x. And that changes in the denominator because now instead of dividing by x like we did up here, we're dividing by negative x. So 4x over negative x is negative 4. Negative 5 over negative x is positive 5 over x. And we can still say that that goes to 0, that goes to 0, that goes to 0. But now our limit is equal to negative square root of 3 over 4, which is the other horizontal asymptote. Over here with g of x equals the absolute value of x plus 4 over x plus 4. Again, we should check both limits. Let's see, we want to find the limit as x approaches infinity of absolute value of x plus 4 over x plus 4. And remember, the absolute value function can be broken down as a piecewise x plus 4 and negative x plus 4. And recall that to find out where the domain breaks, you just set this x plus 4 equal to 0 and solve for x. That'll give you x plus 4 if x is greater than or equal to negative 4. And this is negative x plus 4 if x is less than negative 4. So, since this is going to positive infinity, we're going to, those are numbers that are bigger than negative 4. We're going to replace this absolute value of x plus 4 with this top function, positive x plus 4. So this is the limit as x approaches infinity of x plus 4 over x plus 4, which is 1. And that's equal to y. That's one horizontal asymptote. The other way, the limit as x approaches negative infinity of absolute value of x plus 4 over x plus 4. Well, now since this is going to negative infinity, we want numbers that are less than negative 4. So that means I'll replace this absolute value with this bottom equation, or this bottom function. So this equals the limit as x approaches negative infinity of negative x plus 4 over x plus 4. So now these reduce away and leave you with a negative 1. So y equals negative 1 is the other horizontal asymptote. In this last example, thank goodness there's nothing crazy about this. This is just a rational function. Still want to check both limits just to make sure nothing crazy is going on. So we want x going to infinity of x squared minus x plus 3 all over x minus 3. So again, we're going to use this technique where we divide everything by the highest power of x in the denominator to get something like this. So when we go through and simplify all of these tiny little fractions, you'll get a limit that looks like this. And thank goodness we can get rid of some of these things. There we go, there we go. So this limit simplifies to the limit as x approaches infinity of x minus 1. So we can substitute, theoretically, we can substitute infinity in here for x. And it doesn't matter how big infinity gets, if you're only subtracting 1 from it, you're still going to be at infinity. Let's see what happens when we do the other limit. Limit as x approaches negative infinity. I'm going to start the second limit right here because we're going to do the exact same steps. It's the same function. We're going to divide everything by x. We're going to go here. Actually, I'll start it from here. So the limit as x approaches negative infinity of x minus 1. Well, now we can substitute negative infinity in here. Negative infinity is going to be a really big negative number. Minus 1 more is still going to leave you at negative infinity. Another way you can think about this is this x minus 1 is a linear function that looks like this. Crosses at negative 1 with a slope of 1. And you can think of it like an end behavior problem from a previous course. As x goes to infinity, as we travel further and further and further and further right, the y values keep growing and growing and growing and growing. So if you keep going right, the y values keep growing, that's infinity. Also, if you go to negative infinity on the x-axis, so you're following this line left, 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 it looks like the trend is that the y values will continue to forever decrease, keep going down. Well, they're going to go all the way down to negative infinity. So whenever you do this division by the highest power of x and you're left with something in the numerator like x minus 1, it's really nice to think of it like the end behaviors of polynomials that you may have learned. in previous courses.